Okay, let me introduce this last set of tasks. Here it says the following points will enable the computation of the distribution of the number of times any particular point occurs in a set of sets. So let me give an example, which is the first example here. Suppose we have our big interval, and let's move down here, and we'll take our interval here again. Still working? Still got our interval here, L and L plus 1. We got our points. And suppose we make a sequence of m intervals. So we just lay down m intervals. And they're all of length 1. Now each of these intervals is going to pick out a subset of the points laid down, which is the set S. So what I have is a sequence of m subsets of S. So the question is, for any particular point P, how many of these contain P? And here I can ask that question for all points P. So for each point P in S, I'm going to give a different answer. I'm going to get a different number of these sets containing that point P. So I'll get a histogram when I plot that out. For each point P, I'll have a number, and I can plot those numbers and see how often they occur. So some points may occur 20 times, some may occur 30 times, some may occur 40 times, and then I'd have a histogram like this to indicate the distribution. All right, so just to recap, I'm saying that in my m trials, my m throwing down of, then times I throw down the interval, how many times will that contain P for any fixed P among the points in S? And I'll get a different answer for every different point P in the set S. And then I'm going to plot that histogram. Now, in fact, the distribution that you obtain is a well-known distribution, and I just want to do this to verify that you get a correct answer. But there are other sets that I think are more interesting that can be computed using a similar process that you'll be doing also. All right? So, as I say here, there's a fast way and a slow way to do this, and I'll show you the fast way. So, what you want to do first is you create a vector of zeros of length n, and you call it count point vec. The reason it's length n is, as I mentioned, each point in the set big S will have a different number associated with it. So I need a place to store all of those numbers. So I need big N numbers. Now, remember I'm laying down big M intervals. So I need to loop and look at each one of those intervals. Okay. Now, for each one of those intervals, the leftmost point contained in that interval is going to be your LVEC entry, and the rightmost point is your RVEC entry. So in other words, every index between LVEC and RVEC is in that interval. Every index between LVEC of MM and RVEC of MM is in the mmth interval. Okay, so I should add 1 to the count for every point between those two. And this between is inclusive, right? Because it should include, this is the leftmost index within the set. This is the rightmost index within the set. So this index is inclusive. So I need to add 1 to all of these entries. That's what that particular interval is going to contribute to the total count. So once the loop completes, then you can plot a histogram of the values of count point vec. Right? So that's going to give you the counts that you want. Right? So as I said, that's a well-known distribution. Now, another question that I don't know the answer to, and I think is more interesting, is you have a list of unique sets of the form I intersect S. We created that list. For any particular point P in S, how many of those sets contain P? That's a similar question. Here we also had a set of sets, and we wanted to know the number of occurrences of each P. Here I also have a set of sets, all the unique sets of this form. And for each individual point P, I want to ask the question, how many of those different sets contain the point P? Right? Now, the nice thing is that you can do the very same process, only this time, instead of using all of the intervals that you obtained in your trials, you only use those that give you unique and distinct subsets of the form I intersect S. Now, we have that list. We have UVec. UVec gives me the distinct entries in the list IVec. All right? So if I just take UVec and take UVec and integer divided by n, that's going to give me the leftmost point. UVec mod n, that's going to give me the rightmost point. I can use these two vectors instead of LVec and RVec, do the very same thing, and obtain a distribution of the number of times each point in S occurs in different sets of the form I intersect S. All right, and as I said, I don't know the answer to this question. I'm interested to see if it's the same distribution. All right. So now we can do one more thing. We can look at instead of looking at the distinct sets of this form, we can look at maximal sets. We can ask the question, for any point P in the set big S, how many different maximal sets is that point a member of? And what's the distribution of that over all points P in S? Now, it's really the same question, except that I'm using a different set, a different collection of sets. The way I can get distinct maximal sets is I take LMVec of big MVec. We mentioned above that that's going to give me all of the leftmost points in maximal sets. And RMVec of MVec gives me the corresponding rightmost points of those same maximal sets. All right, so I'm going to do the same process, only instead of using LVec and RVec, I'm going to use LMVec and RMVec. All right, and then I'm going to call my resulting vector this one, and this gives the distribution of the number of distinct maximal sets that contain each point. So it'd be interesting to compare these three distributions. All right, so that's your third task.